in this example, I'm going to find the distance between a point, in this case, this point A, and a line, which is also given. So I know a point on the line and its direction. So this point and this line, when I talk about the distance between it, of course, I mean the shortest distance. So I'm really after this perpendicular distance here. I'm going to start, though, by finding a vector from the point A to a general point on the line. And this point is going to be able to move along depending upon the value of lambda. So I want to find the vector A to P, which I can find by doing vector P minus the position vector of A. If P is a general point on the line, then its position vector is this. So 1, 2, 3 plus lambda 3 minus 1, 2. Subtract position vector of A, which is 4 minus 3, 10. So I can work that out. 1 minus 4 is minus 3 plus 3 lambda. Look at the middle row, I'm going to get 5 minus lambda. And looking at the bottom row, I've got 3 minus 10 is minus 7 plus 2 lambda. So that's the general vector from A to P. Now, P will move along here depending upon the value of lambda. I want to find the value of lambda such that P actually ends up in this position here. So we actually require AP to be perpendicular to the line. Now, I know a vector in the direction of the line. It's given by 3 minus 1, 2 is the direction vector. So I require AP to be perpendicular to 3 minus 1, 2. And this is where I can use the scalar product to fix these to be perpendicular. So I need minus 3 plus 3 lambda, 5 minus lambda, this is the vector AP, minus 7 plus 2 lambda, dotted with 3 minus 1, 2 to be 0. And this will lead me to the value of lambda, which makes them perpendicular. So let's do this. So I've got 3 lots of minus 3 plus 3 lambda plus minus 1 times 5 minus lambda plus 2 lots of minus 7 plus 2 lambda equal to 0. I'll leave you to work through the expansion and the solution of that. That leads me eventually to lambda equal to 2. So what that does, it gives me the value that places P there. If I use lambda is 2, I know that I'm talking about that distance. So I can now find A to P when lambda does equal 2. A to P is the vector I'm going back up to here. This is my vector A to P from before, is equal to minus 3 plus 3 lambdas, that's 3 lots of 2 is 6, and 5 minus lambdas, 5 minus 2, and minus 7 plus 2 lambdas plus 4 gives me the vector 3, 3, minus 3. Therefore, the distance A to P is the length of the vector A to P is the length of this. 3 squared plus 3 squared plus minus 3 squared is 3 nines root 27, or 3 root 3.